I'll begin with a very quick recap of what we have done so far, a very brief summary. So we saw that at the end of the evolution of massive stars, you have a compact star like a neutron star formed. And the amount of matter that will condense from the core to form a compact object actually depends on the initial mass of the star, because the size of the core that goes unstable from thermal pressure support is proportional to the mass of the star itself. So that's then decides what is the final compact object, and we are looking at the range of compact objects which are which form neutron stars.
As such, you will not be able to. You have to do repeated observations.
Is there a question? Okay, so then the mass of the neutron star has an upper limit that is given by the equation of state, and for most equations of state, we find that the upper limits are around 2.5 solar mass. There are, of course, equations of state which even give you smaller upper limits, and as more mass measurements in the range of 2 solar mass come in, some of those equations of state we know are no longer valid. So typically, the upper mass limit of a neutron star will be around 2.5, or maybe between 2.5 to 3 solar mass. So we don't know exactly because we don't know the equation of state exactly. And the uncertainty in the equation of state also causes us to not really know the composition of the very center of the neutron star, where different types of particles, hyperons, mesons, quarks may exist, and depending on what exists, that will decide the mass, radius, as well as other properties like cooling, viscosity, tidal deformability. All of that depends on the full equation of state of the neutron star. So therefore, there are multiple observables which in principle can be used to constrain the internal structure as well as the equation of state. The free neutrons in the core plus the free neutron drip neutrons in the crust form a superfluid, and the superfluid carries angular momentum in Onsager-Feynman vortices. In the core, the Onsager-Feynman vortices also acquire a magnetic field because of two reasons: because the neutrons are paired in a triplet p state, so their spins are aligned, and also because the flow, superfluid flow, entrains local protons, and if you have a charged fluid which also is given circulation, you also get a magnetic field. So the vortex cores create magnetic fields of the order of 10 to the power 15 Gauss. And the regular magnetic field itself is carried by the proton superconductor in the interior, which is in the form of abricos fluxoids, which have each of which has a quantized flux unit of hc by 2e in CGS. And that gives you a large number of fluxoids for typical magnetic field. So, and some of these things you already did yesterday in the tutorial. So today, with this background, I will very briefly introduce oscillations. Next week, you're going to have a much more detailed discussion in rapidly spinning neutron star session of all of these effects. So I'll do this just for the sake of completeness and just to make connection with what we have said before, and then I'll move on to binaries. So a neutron star is more or less a spherical object, and any defined entity like this can have its own normal oscillation modes, right? So this object can oscillate in many ways. It can have radial oscillations. It can have non-radial oscillations where you have spherical modes, but there are also motions which are not necessarily radial. And then you can also have shear modes, which just is the torsional mode of the star. And all of these will leave signatures in the radiation that is produced by the neutron star. So if the neutron star is radially oscillating, then the electromagnetic radiation that you get from it will bear some signature of that oscillation. So if you are able to analyze that intensity as a function of time, you should be able to see the imprint of such oscillations. Except most oscillations that you excite in a star like this is going to be damped pretty quickly. And that's because there is the material inside has a finite viscosity. And this finite viscosity arises from scattering, for example, neutron-neutron scattering. The scattering of electrons from all the components, as I described yesterday, the vortices in the superfluid core have a strong magnetic field, and electron scattering from there creates a very strong viscosity, so very strong coupling of the superfluid core with the crust. And so there are various mechanisms of shear viscosity as well as bulk viscosity. Bulk viscosity occurs because if you squeeze the neutron star, for example, then you have now, at a given radius, you now have a Fermi energy of neutrons and protons, which are now different from the equilibrium value. So that means there will now be some conversion between protons to neutrons or vice versa, and to restore beta equilibrium. And any such process, as we have seen, creates neutrinos or antineutrinos. And these neutrinos or antineutrinos will typically leave the system. Therefore, there is an energy loss, which is basically akin to viscous dissipation. So you have bulk viscosity, you have shear viscosity. And these things will tend to damp any oscillations that you generate in the star. Now, any oscillation mode, let's say this is radius r, and any oscillation mode can be written in terms of the kind of oscillation amplitude function, which, as all of you would have done in quantum mechanics, in spherically symmetric problems like this. So let's say you have the oscillation function, which is a function of r theta phi. So this can be written as a radial function, which can then be represented by the number of nodes it has. So it's Rn, a function of r, and then you can use spherical harmonics to represent the theta phi times some coefficient CLM, which is the amplitude. So this is a general description of any oscillation mode that you can excite in a star like this. And depending on the kind of eigenfunctions that you are talking about, these modes are classified into various types. The fundamental mode, or F mode, is one where the radial wave function has no nodes within the star. So n equal to 0 mode. The restoring force for F mode is primarily the pressure perturbations, but assisted by gravity. There are modes which are of frequency significantly lower than F mode, which go deep into the star. They're called G modes. And modes which oscillate faster than F modes and are located closer to the outer parts of the star. There the restoring force is primarily pressure perturbations. They are called P modes. And if these modes get generated, there are frequencies which you can calculate given the structure of the star. Then you can identify the frequencies in the oscillation and then work back and try to reconstruct the equation of state. That's the structural property of the star. Except, as I said, even if these modes get excited, they are not long-lived, unless there is a source which is pumping these modes. Have we seen such oscillations? One clear case where many of these oscillation frequencies have been seen is the 2004 hyperflare of the soft gamma repeater SGR 1806-20. So it's a magnetar. It's a star with a very strong subsurface magnetic field. And once in a while, the twisted structure of magnetic field, which is subsurface, relaxes. And as it relaxes, it causes a big crust quake. And the star is set into oscillation in all its normal modes. And this was a very bright flare. And then after the flare, as the radiation declined, one could see many oscillation modes in the radiation, the intensity as a function of time. And they have been identified with various modes like this. But that's the only case we know where we have a large number of these modes identified. And after a while, both this radiation from the outburst died down, and the steady quiescent emission from this, whatever amount has been seen, do no longer carry the oscillation signature. So that means this oscillation also died down. So we have to wait for another such big flare in one such object to be able to further study such modes. However, in case of yes.
For this source, how were these oscillations observed?
It's in electromagnetic radiation.
The X-ray spectrum.
X-ray, yes. In X-ray, and it also had optical ultraviolet. So it was largely in X-rays. You saw these quasi-periodic oscillations. Now, if you take such a neutron star, or take two neutron stars and put them in a binary system, and have the binary system of very short separation, then the neutron stars will feel tidal forces to each other. So you will get a tidal deformation of the neutron star. And that is stressing the material which is present here. Now, if you have the binary orbit with even a tiny eccentricity, then you will have the material being stressed periodically, periodic variation of stress at the orbital period of the binary system. And this forcing can excite some of these modes, particularly the F mode, when the separation is very close. So, why particularly the F mode? Because F modes are the lowest frequency modes among the surface modes. So, P modes are also closer to the surface. F mode also, the energy resides closer to the surface. And G modes are much deeper in. So, the tidal deformation is felt more near the surface than deeper in. So, and to resonate with P modes, you have to go to even higher frequencies. That means the orbit has to become even faster. So, F modes are the typical modes which you can excite in such binary systems. So, this probably can be seen if we have enough sensitivity in a compact binary coalescence just before the coalescence. I presume there are efforts which are going on in trying to extract this from the waveforms, but I am not aware of definitive detection of F modes yet from compact binary coalescence. But even this is more or less a transient excitation. You have this, then coalescence occurs, and then this is not there anymore, and this lasts for a short while. So, can there be a situation where you can have a long-lasting excitation of any oscillation mode of the neutron star? And that's where modes like R modes become important. So, R modes are purely toroidal modes. Okay, so, they are not, they don't have any radial oscillation component. But, so if you just take a look at the surface and spread it out, then so theta going from, let's say, one pole to another pole over here, and phi going around the star, then you will have material circulating like this. So that's the way the R mode instability works. The material on the surface will undergo circulations like this, and then number of nodes here is the azimuthal quantum number m, azimuthal order m. Yeah. No, this is, these are opposite directions, no? These alternating directions are opposite. So, so now, these R modes have you will, I'm sure, study it in more detail next week. But just to give the basic properties, the frequency of R mode, let's call it omega R, is roughly equal to, should I write it correctly? Is the other way around? This is this way. That is that way, right?
They're both clockwise, right?
This is clockwise. Oh, yeah. This has to be the other way around, right? Yeah. This is anti-clockwise. No, this is correct. This is anti-clockwise. No. This is anti-clockwise. This is L equal to 2, right? So this is anti-clockwise, so this will be clockwise over here. Because if you roll it back, then the material flow here is downwards. This will have to be upwards. Okay, right. Correct. So this is this way, and this will go up. Yeah. So frequencies are given by 2m omega divided by L times L plus 1 times 1 minus a dimensionless number omega 2 times r cubed omega squared over g. So leading order frequency actually has no dependence on the equation of state of the neutron star, because it just depends on the rotation speed. But this quantity, the first order correction, the next order correction, has a dependence on mass and radius. So that, so if one can analyze the R mode frequency well and compare it with omega, then one should be able to find a constraint on the equation of state from this. Omega 2 is a number which depends on the density profile, in fact. So you have to compute an integral over the whole star, and that will give you omega 2. This is a number which is typically less than 1, between 0.4 to 0.8, roughly, for different types of density distribution. So this is one way one can derive constraints on the equation of state if you can find R mode frequency. So if an R mode oscillation is ongoing, why should it be not damped? Why should it be ongoing for long enough time for us to be able to see it? And that's where a very interesting aspect of coupling between gravitational waves and neutron star oscillations come about. So now, if we look at this pattern, so this pattern has, as I said, is a toroidal mode, so it has got a motion in phi direction. Yeah. Material, this is the direction of material velocity, which is giving you the mode oscillations, right? So this is not a mode where the material is going in and coming out. They're only moving on the surface, but it's moving in this circulation pattern. This is at the surface of the crust. Yeah. So now, this pattern is actually moving on the star. Note that this mode will not be there unless there is an omega, right? So it's only relevant for rotating stars. If you look at an observer, if an observer who is co-rotating with the star looks at this motion of this pattern, then the rotation speed that the observer will see is minus 2 omega which means if the star is spinning in a certain direction, the pattern is moving in the opposite direction. It's a counter-rotating pattern for any observer who is sitting on the star itself. With respect to stellar surface, this pattern is moving backwards compared to the stellar rotation. But if you look at how this is going to look to an inertial observer who is outside the star, then of course you have to add omega to this. For inertial observer, external observer, the sigma I will be positive. This quantity is less than omega. The main modes will start from L equal to 2 and then go up. So this will be omega times L minus 1 times L plus 2 divided by L into L plus 1. So here is a situation where the pattern, as far as the star is concerned, is retrograde, but as far as the inertial observer is concerned, it is prograde. The restoring force of this is actually the Coriolis force on the surface of the star. Yeah. No, it's this is, I mean, you have to have e to the power of I for each of these. You can will have a e to the power of I omega t. I only wrote the amplitude of it. So, so any such wave which creates density perturbation on the surface and is retrograde on the for a star-bound observer and prograde for an external observer is subject to what's called the CFS instability. This is Chandrasekhar-Friedman-Schulz instability, because the mass perturbations, which the density perturbations which this causes, adds to the mass quadruple moment of the star. And now since the star is rotating, the star rotating with the finite mass quadruple is going to produce gravitational waves. And these gravitational waves are going to take away angular momentum, right? So if the gravitational wave is taking away angular momentum, then it's trying to slow down the motion of this pattern. However, looked at it from the point of view of the star, this is like adding a negative rotation to the pattern that is already rotating in the negative direction. So instead of damping the oscillation by taking away angular momentum, it is going to actually add to that. So this is a positive feedback to the oscillation, and the oscillation will continue to grow, but of course it will saturate when the rate of growth and the dissipation come to an equilibrium. So in such a situation, you will have an unstable R mode, which will then, once you excite it, it will continue to retain its character on the neutron star surface, and it can continue to generate gravitational waves. So the CFS instability is a common phenomenon not just for R modes, but for any other type of perturbation on the surface, which is retrograde in the star's frame, but prograde in the external frame. So given this, then one would expect continuous gravitational waves for stars for which such R modes can be sustained. The limiting factors are going to be dissipation again, right? So although you have forcing which is happening due to gravitational wave, it will still have to overcome the internal dissipation that is happening within the star. So that happens for certain parameter ranges, and exactly what parameter ranges for which this happens is still a little bit open, and it will depend on also the stellar structure. But typically you would find that if you have, let's say we plot omega over here, and temperature, because viscosities in the interior depend on temperature. And this is the maximum. Omega k is the maximum speed at which the neutron star can rotate. After that, it will start shedding mass from its equator. So you typically have a region like that, within which R-mode instability is possible. Below this, it is damped because of viscosity. You have shear viscosity over here, bulk viscosity on this side, which are responsible for damping out the oscillations. Typical numbers here, this is something like 30–40% of the fastest possible rotation. And this temperature is close to 10⁻⁻10 Kelvin. A typical neutron star, as we have said, will have an interior temperature of 10 to the power 8 Kelvin or so, so that will be somewhere there. And this omega is something of the order of 0.5 or 0.6 omega, let's say, omega k. So that means if the neutron star is spinning very fast, typically omega k here will correspond to period of the order of half a millisecond. So this is something like a millisecond or so. Millisecond to 1.5 milliseconds. So in that range, for an interior temperature, comfortable interior temperature of 10 to the power 8 Kelvin, you will have armored oscillations. Now, once these armored oscillations are present, the neutron star is going to lose angular momentum, not only due to the electromagnetic torque that I was talking about yesterday, which spins down the pulsar, but also due to gravitational waves. This combined torque is going to spin down the star quite rapidly. So as long as the armored oscillation is active, you will have a fast spin down of the neutron star. But once the armors get damped out, then this mechanism is no longer going to operate. If you have other sources of gravitational waves, like permanent ellipticity due to magnetic field or something like that, that will still continue to operate. But this operates only when the star is spinning very fast. But if one can identify objects like this and use gravitational wave detectors to integrate for a long time, then it may be possible to detect continuous gravitational waves from armored oscillations. I'll not say anything more than this because you're going to have a full course next week. Any questions? Because now I'm going to move to binary systems. No. So, for example, G modes go deep into close to the center. P modes are closer to the surface than G modes, but the radial function still has existence in a significant part of the star. R mode is almost entirely at the surface.
But that is independent of what is happening inside the star. I was thinking like if the vortices are oscillating, that doesn't contribute to any oscillation outside.
Okay, so if the vortices are oscillating, you will have to find a way to transmit that oscillation, information of that oscillation to external world, right? So it will have to come in through some density oscillations or pressure oscillations, which will then excite oscillations on the surface through a P mode or something like that, right? Any matter inside, if it oscillates, it will then feed into one of these modes, which are of the right frequency, which will resonate with that. Right? There are very, very large number of modes possible, right? You just change your order numbers. You can get a very large set of modes. And depending on your excitation frequency, one that is closest in resonance, and that will really become prominent, right? Yeah. Yes. It is because, even if the pattern was stationary on the surface, because it is spinning, it becomes time dependent. Consider a frozen pattern of density variation on the surface and then rotate it. That is good enough to detect, good enough to generate gravitational waves, as long as the frozen pattern has a non-zero quadrupole moment. Does that answer your question? This is how even a magnetic deformation is able to produce gravitational wave, right? Because it's got a quadrupole moment and you're spinning it. Okay. So let's now go to binaries. Study of stars in binary systems is very important because almost all stars, when they're born, they're either in binaries or in multiple systems. It's in rare occasion that the star becomes single. So more often than not, the stellar evolution is affected by the presence of a binary companion. If it happens to be a multiple system, there are stars, in some fraction of stars, which remain in multiple systems for long periods in their life history. But in most cases, even if a star is born in a multiple system, they usually split up into pairs. So if it's a triple system, usually the least massive star will get ejected from the system, and the system will remain as a binary afterwards. So binary systems are seen everywhere. The effects due to binary evolution are also seen very ubiquitously. So let's start with some basic description of a binary system, where you have two stars, one of mass m1, one of mass m2. They're rotating around a common center of mass, right here as Cm. Ignoring everything else in the universe, if I take a point somewhere in the vicinity of this and ask what is the gravitational potential, what is the total potential at this point, if the observer here happens to be rotating, co-rotating with the binary system. So take a point which is co-rotating with the binary system and ask what is the potential that the observer there will experience. So let's say the distance of this point from M1 is R1, from M2 is R2, and from the common rotation axis, it is R3. So the potential that the observer here will experience is minus Gm1 over R1 minus Gm2 over R2. But this is co-rotating with the system. So in addition to the gravitational forces, also centrifugal force is experienced. And that in such a system can be, the centrifugal force can be written as the gradient of a potential, which is omega squared R3 squared by 2. This form of potential is known as the Roche potential. See, if I were to draw this potential, I take the last term and then start somewhere there, because the scale of the potential is arbitrary. So the zero of the potential is arbitrary. So I will start there, and as you can see, it is going to drop parabolically on both sides of the center of mass, that is this term. This is a mass that is closer to the center of mass, which means this is heavier. So at this point, I have the heavy mass. So I then have a deep potential well over here. And at this location, I have a smaller mass. So I have a less deep potential well over there. So I've added these three components. So I have a net potential curve like this. If the binary happens to be close, then these two will start getting closer to each other, and you will see a net potential which will look like this. Remember, there are two stars. One star is sitting here, one star is sitting there. They're spinning around a common center of mass which passes through this point. Now, stars, as we know, in the course of their evolution, they expand. This is a potential well, and let's say the initial radius of the star is over here. Initial radius of this star is over there. As evolution proceeds, the star is going to expand. So that means it is going to go up in this potential well. Because half of this is the radius of the star. As it expands, it rises here. At some point, if the star becomes as large as this, then if any further expansion is going to cause material to go from this star and fall into the other star. And this can happen also for the other star if that star is evolving. But in general, if you take stars of different masses, the heavier star evolves first. In main sequence, the main sequence lifetime is roughly proportional to 1 over the cube of mass. So if you take a star which is twice as massive as the sun, its lifetime is 1/8 that of the sun. So that's going to evolve much faster. That's going to start becoming vulnerable to transferring mass onto the other star. So we'll then call this star a donor, call this star an accretor. So this diagram is usually depicted in the equatorial plane of the binary system. So where, if I take a cross section and then plot contours of this potential, then you will have M1, you have M2, and you will have so this value of the potential, if I draw equipotential for that value of the potential on the equatorial plane, then it will look like this. So this is a three-dimensional equipotential, you can think of that way. And this is the equatorial cross-section of it. The equipotentials which are inside this are centered on the star. You'll notice another thing. Suppose the star expanded and expanded beyond this point, then the material is actually going to leave the system. You have an outflow here or an outflow there. So equipotentials for those, one can draw as well. So you have and then I have this. And then you will have further equipotentials which will just be encircling this and then keep going down. Inside here, you will also have equipotentials like this. You clearly see that you actually approach an inflection point here and there. So there are these special points in the potential. 1, 2, 1, 2, 3, 4, 5. These are called Lagrangian points. So this is Lagrangian point L1, L2, L3, L4, L5. So of these Lagrangian points L1, L2, and L3 are critical in determining how the binary system evolves with time. As we already said, that suppose the M1 star expanded and it filled this equipotential. The stellar surface is always an equipotential. If the stellar surface was not an equipotential, then there will be material movement on the surface itself because it will feel a force. So stellar surface is always an equipotential. So the surface will move from one equipotential to the next equipotential to the next equipotential. At some point, it is going to hit this equipotential. As soon as it hits this equipotential, then the material is going to be transferred to the other star. Now this star will then experience a loss of mass. So as a mass is lost, depending on the evolutionary state of the star may shrink because you have taken mass away. Or if it is in a phase where the internal processes are actually making it expand at a rapid rate, then even if you take away some mass, it may continue to expand beyond this. Right? But whichever amount of matter tries to go beyond this is going to be captured by this other star. So these critical surfaces are some of the most important factors in binary evolution. These are called Roche lobes. And as you would realize that the Roche lobe around a more massive star is larger than the Roche lobe around the less massive star. And the size of the Roche lobe clearly depends on the separation. It's actually proportional to the separation. You take the same two stars and make the separation larger, this whole diagram is going to scale up accordingly. So what is the consequence of this kind of evolution? As we said, if you start with a binary system of this kind, where you have a mass ratio a little far from 1, you have a more massive star, let's say a 20 solar mass star, and you have a less massive star, let's say 6 solar mass star or 8 solar mass star. If these two stars were evolving independently, there was no exchange of matter, then the 20 solar mass star will end up producing a neutron star and undergoing a supernova explosion. The 8 solar mass star is going to produce a white dwarf and generate a planetary nebula. But that fate can be altered in a binary system like this. So as this star evolves, which is close enough, then in the later stages of evolution of the 20 solar mass star, matter can start getting transferred onto the other star. And since this expansion is driven by the internal shell burning and core contraction and so on, just by taking away the mass from the surface, the expansion is not going to stop. So it is going to drive this until more or less just the dense core of the star is left. So a 20 solar mass star may then be left with only about 3 or 4 solar mass core. The rest of the matter would have gotten transferred to this if there is no mass loss from the system. So let's say 20 solar mass star transfers 15 solar mass onto the other star, and then is left with 5 solar mass. The other star, which started as a 8 solar mass star, has now become a 23 solar mass star. So its evolution is going to be altered because it was actually relatively early in its stage of evolution when it got this extra mass. So it had not yet matured. It was still burning hydrogen at the center. And it was going to happily accept this extra matter, and then it will start behaving now like a 23 solar mass star, and eventually it is going to produce another neutron star. In the case of the first star, although it has transferred its envelope, its core evolution had already proceeded to practically the maximum extent. So this will undergo a supernova. It is not going to eject the full core minus 20 solar mass in the supernova explosion. It will only eject whatever amount of matter remained in the envelope. But it will still produce a neutron star because it was already set on the path of producing a neutron star, and only in the late stage, the envelope matter, which would have been ejected anyway, has been transferred to the other star. So this system, at the end of this evolution, is then going to end up producing 2 neutron stars in the same system, instead of just producing a neutron star and a white dwarf. So mass exchange is extremely crucial in determining the course of evolution of closed binary systems. And many of the objects which are of interest in gravitational wave astronomy today have been deeply affected by the interaction in closed binary systems. So let's take a brief look at how the orbit may evolve. The one quantity that we can write for a Keplerian system like this is the angular momentum in the orbit, which is given as m1 times m2 times square root of GA over m. So A is the separation. And square root of 1 minus e squared, if the orbit is eccentric. So I can take logarithm of both. Okay, so what is m? M is just the sum of the total masses. So and then write a logarithmic derivative is m1 dot over m plus m2 dot over m2 m1 dot over m1, m2 dot over m2 plus half a dot over a minus half m dot over m then this will give me E dot over minus 2 E dot over 1 minus e squared. So we can collect all this and then write an expression for A dot over A in terms of all these changes. So A dot over A is 2 J dot over J minus 2 M1 dot over M1 minus 2 M2 dot over M2 plus M dot over M plus 2 E dot over 1 minus E squared. Made a mistake here. So now we are in a position to describe what happens to the orbit if mass is transferred or lost from the system. This is a fully general expression. Now, as mass is being transferred to the other star, if the expansion of the primary star is very high, then the matter may not be contained in the Roche lobe itself. The matter may overflow the Roche lobe and then escape through the second and third Lagrangian points. That means that there may be a loss of mass from the system. There are other reasons too why mass may be lost from the system. One is stellar winds. We know all stars lose mass in stellar wind. Even our sun loses mass in stellar wind. It's a small amount of mass, 10 to the power minus 14 solar masses per year for our sun. But if you go to more massive stars, the mass loss rate becomes much larger. And in the phase where the star is less gravitationally bound, that means the surface has expanded to larger sizes, the mass loss rate in the wind actually goes up. So there could be a substantial mass loss rate, A, due to the wind, B, due to the fact that it may be overflowing its Roche lobe and then losing mass through the second and third Lagrangian points. So whatever be the reason, there is yet another limitation on the mass acceptance which exists, but we'll come to in a short while. So let us say that I have the star M1, which is the one which is losing mass, right? It is losing mass to the companion, and it may be losing mass also from the system. So if a fraction alpha of the mass is lost, then I can rewrite this as minus 2 times 1 plus alpha minus 1 M1 by M2 minus alpha by 2 times M1 by M M1 dot over M1 plus 2 J dot by J plus 2 E dot over 1 minus E squared. So here what we have done is we have said d M1 dt is m1 dot, which is negative in this case. dm dt as the total mass of the system is alpha m1 dot. Fraction alpha of the mass being lost by m1 is being lost from system altogether, and dm2 dt is 1 minus alpha times m1 dot. Minus. So if alpha is 0, then the entire mass is going from m1 to m2. The quantity m1 plus m2 remains constant if alpha is 0. dm2 dt is minus m1 dot. dm1 dt is plus m1. So, but m1 dot itself is a negative quantity. So one can use this general expression now to find what the orbital evolution is going to be for different combinations of alpha and m1, m2, etc. But remember, there is also this quantity 2j dot over j. So this represents the loss of angular momentum from the system. Why would the system be losing angular momentum? Is the net angular momentum of the binary being lost? Give me at least one reason. Change of momentum of inertia does not cause angular momentum to be lost from the system. How? Angular momentum is in general conserved, right? You have to have, if you change momentum of inertia, your angular velocity is going to change accordingly to keep angular momentum conserved. Go ahead. Due to? Mass leaving the system. Correct. So you're expecting that the mass that is leaving the system is actually carrying some angular momentum with it. It may or may not, but yes, in general it will. If, for example, the mass is being lost directly from m1, then the star m1 has a specific angular momentum, the angular momentum per unit mass. You can take the angular momentum per unit mass of the component m1 and take alpha m1 dot, multiply by the specific angular momentum. That will actually give you the rate of angular momentum loss from the system. Can there be angular momentum loss from the system when alpha is 0? In this school, I am expecting an instant answer. Gravitational waves, right? So gravitational waves is another agent which causes angular momentum to be lost from the system. It is important when the binary separation is very small. Otherwise, magnitude-wise, it is quite insignificant. And for binaries of regular stars, for example, it is not a very strong effect. But if one of the components of the binary system is a compact object, then it becomes significant. So there are two ways of angular momentum loss we have discussed. And a little bit more of a additional mechanism of loss of angular momentum associated with the loss of mass is to do with stellar winds. The stellar winds going away from a star carries not just the specific angular momentum of the binary, specific orbital angular momentum. Even if the star was single, like the sun, and we see solar wind moving out, does the solar wind carry any angular momentum? It does. It's a plasma that is flowing out from a star which is spinning and has magnetic field. So the plasma that is streaming out, it carries a frozen magnetic field, and as it moves out, it exerts a magnetic torque on the sun, which will tend to spin the sun down over time. Okay, so this is called magnetic braking. So the spin frequency of the mass losing star in general is going to be reduced due to the angular momentum being lost, angular momentum carried by the magnetic stellar wind. But how does that affect the orbit? Yes, the star is going to spin slower and slower. How does it matter? Would it affect the orbit? Due to spin? So that will have to be the orbital angular momentum to carry away, right? So if you carry away spin angular momentum, is that going to affect the orbit? Is the question. As it turns out, it does, and it does significantly. The reason is these two stars are in strong tidal interaction. When you have this big objects in tidal interaction, these extended objects in tidal interaction, if the spin of the star and the orbital angular frequency are not the same, then what happens is that the tidal interaction raises a tide, and that tide tends to move away from the line joining the two stars, because the other star is spinning at a frequency which is not locked to the orbit. So with respect to this diagram, which is spinning at the common orbital frequency of both the stars, now this star has a spin. So in this frame, this star is spinning. You raise a tidal bulge on this star, and that will tend to move away from this line. As it tries to move away from this line, it is now going to feel a torque, because you have some extension like that, and obviously there's going to be a tidal torque on it, which will try to bring it back. And this torque is going to go in the direction to always try to bring the star in co-rotation with the orbit. So if the star is spinning faster than the orbital period, then angular momentum is going to be pumped into the orbit due to this tidal interaction. And we see this happening right here. The Earth-Moon system, the Moon has already locked its spin to the orbital period. The Earth hasn't. The Earth is moving much faster than the orbital period of the Moon. And the Moon raises tides on Earth. And these tides then go towards transferring part of Earth's angular momentum into the orbit. As a result, Earth-Moon orbit is getting wider with time. 4 centimeters a year is the rate at which the Moon is receding from us. So that's the same effect. So now assume that this has already happened. These two stars are locked in rotation with the orbital period. Now, the magnetic stellar wind from this star takes away spin angular momentum of the star, therefore tries to spin it down, which means once that happens, this star is now going to rotate slower than the orbital period, because the spin angular momentum is being lost in the magnetic stellar wind. And of course, as soon as that begins to happen, the tidal interaction is going to restore the spin back to the orbital period. So this tidal interaction is going to pump some of the orbital angular momentum into the spin of the star, so that the star spin can come back into synchronization. And then magnetic stellar wind is going to take away that extra orbital angular momentum that was delivered to the star in trying to synchronize it. So what then happens is that although the magnetic stellar wind is carrying away the spin angular momentum of the star, since the spin angular momentum is being fed by the orbital angular momentum, so this becomes an agent of depleting the orbital angular momentum. So magnetic stellar wind slows down the spin of the star, orbital angular momentum is pumped into it so that it gets spun up to maintain synchronicity with the orbit, and then again magnetic stellar wind takes away some of this spin angular momentum. So it continuously happens. So as a result, the star remains locked to the orbit, but the orbital angular momentum is effectively lost. So this is what is called a magnetic braking. And this could be very important in the evolution of binary systems, closed binary systems containing a compact star and a regular main sequence type of star. I think this will be a good point to stop today. I'll continue from this tomorrow. So what we have seen today is, in a binary system, stars interact tidally. That tidal potential can be expressed in the form of this Roche potential. and that Roche potential then reveals the conditions in which mass transfer can take place from one object to another, and as a consequence of the mass transfer as well as loss of mass from the system, how the orbit of such a system is going to change with time. We will see one or two problems in the tutorial session today, also basically using this. And then we'll continue from this in the next lecture.